Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. In this video, I'm going to go through a typical quiz problem for applied mechanics and design. So let's have a look at the problem. Okay, so here's the problem. So we just have this truss frame here loaded with two forces and a moment applied at the end here. Note up here that this is not going to be a truss analysis problem where you have to do method of joints or method of sections. We're just going to treat this as a rigid body and just look at the external actions for now. So part one of the problem is for the idealized model of this truss frame that we have here, determine the reactions that these supports here exert on the frame. And then part 1.2 is to do a check calculation to check your answers. So whenever we do an engineering mechanics problem, we should always think about our answers and try and do some check calculations. So part of the quiz is to do that. So for example, in part 1.1, if you did the normal thing where you use one moment equilibrium equation and then two force equilibrium equations, then do your check by using another moment equation about some other point. Then down here, so at the moment we've just got these letters here representing the loads, and we're given the magnitudes of these forces and moment over here. So in the quiz, every student will have a different value for these loads depending on their student number. Okay, so that's the equilibrium part where you look at determining the reactions. And then second part is to look at equivalent forces and moments and the equivalent single force. So to start with, for the three loads shown, determine the equivalent single force and moment at the pin connection. So up here. And then after that, determine the equivalent single force. So no moment, just a force only. What's the equivalent single force? And indicate its line of action that gives us the same loading, external loading, as what we found in 2.1, and also that we had to start with our three separate loads here. And then part 2.3, use the equivalent single force that we found here in part 2 to determine the reactions again. So basically redoing part 1.1 to determine these reactions, but this time we're just going to use that single force that we've found to be equivalent to the original loading. So part 2.1 to 2.3 goes through equivalent systems, equivalent force, moment systems, but also shows you a way to check your calculations that we did up here. All right, so let's have a look at the solution. I'm just going to change the window that we're looking at here. I'm just going to use my iPad to do this, so I'll be looking down a little bit if you're wondering why I'm looking down. So thinking about our solution plan, as usual, we're going to draw the free body diagram, apply the equations of equilibrium, solve those equations for our unknown forces, and then we're going to check our answers. Firstly, drawing the free body diagram. Again, just a simple representation of the outer shape of the body that we're analysing. So in this case, it's a truss frame, but we don't have to worry about the internal members. In this case, we're just going to treat the whole thing as one rigid body. So that's what I've drawn there, and I've put on the dimensions. And then I start putting on my loads. And that's usually the easiest place to start when drawing your free body diagram and starting to think about the loads and the other forces and moments that are acting on the body. So we have that. Now we need to think about what's happening at the supports. So at the support up here, at this point here, I'm going to give them names in a second. So in the quiz, in this particular version of the quiz, I didn't have any because I left it to the students to come up with their own letters. All right, so up here we've got a pin connection. So at a pin connection that's fixed to the ground, we'll have a vertical and horizontal reaction force. All right, that could be in any orientation. They don't have to be vertical and horizontal, but because all of our dimensions are vertical and horizontal, that's the most sensible direction to have our reactions. So I've just put that in, and I haven't put the arrowheads on yet because yeah, I'll think about which way they might be, or I can just assume them all positive. So here you can see I've decided to take to the left for the horizontal component. Right, so what I would have done here was to imagine taking moments about this bottom point here, right, bottom left-hand corner of the truss. So right, what's happening with my forces and moments that are acting on this? They're all tending to cause a clockwise rotation about this point here. Right? So P1 will tend to cause clockwise rotation about this corner. M1 is clockwise, obviously, and this force here, P, its vertical component at P1 will tend to cause a clockwise moment about this point, and the horizontal component of P1, its line of action passes through this point, so it has no moment reaction. So for this thing to be in equilibrium, this reaction force up here must be acting to the left. Right? If you do the problem with it shown acting to the right, you'll just get a negative value in your answer. All right, so that's point A, and we're now going to name our unknown. So I'm going to call it here RAY, RAX. In many textbooks and other people's solutions that you might see, they might just call this AY and AX. That's okay, but I tend to prefer using R or F just to indicate clearly that it's a force. Because when, if you wanted to make this a parametric problem and have parameters for these dimensions rather than specific numbers, then you'll be wanting to use letters to describe those dimensions. But anyway, that's another video. All right, so now that we've started using X and Y components, we should really indicate what X and Y are. It's fairly obvious from my diagram because I've drawn it nice and neat and clear, and Y is obviously going up or down, and X is going horizontal, right? So here I've shown the positive sensors and the directions for X and Y. And I've also indicated that anti-clockwise is going to be positive for my moments. Right, so looking down here at this point here, I've already started the solution. Right, what do I put down here? If I look over here, I can see over at the bottom left-hand corner of the truss, I've got a roller support, and that roller support is sitting on a sloped surface. And for a roller support, we only have a reaction force that's normal to that surface, none tangent to the surface. So that's what gives me this direction of my reaction force over here. Right. I don't have the sense shown yet. How would I work that out? If I took moments about this point up here, so about point A that I've now labelled, this force here, P2, is tending to cause a clockwise rotation. M1 is causing a clockwise rotation. P1 is causing a clockwise rotation about this point, about point A. It's a bit tricky. The horizontal component of P1 here would be causing an anti-clockwise rotation. But on the balance of things, it's probably more likely that we need an anti-clockwise moment from this force. So I've put it shown acting upwards and to the right. And I've also just copied over here my angle that force acts at. Okay, so that's my completed free body diagram. Now I can start to write my equations of equilibrium. Oh, not quite complete. Label my unknown force here, RB. So again, I've used R subscript B rather than just B, just to be clear that this is a force, not the point B that I'm referring to when I write my equations down here. All right, so just putting on my solution there for reference, the magnitudes of those forces that we were given, applying equations of equilibrium, starting with a moment equation. Generally, you would start with the moment about a point where you've got two unknowns. Here, we could have started with point B, taking moments about point B because RAY passes through point B, so you can find RAX directly. But you can do that as an exercise or do that as you check. All right, so for this solution, we're doing sum of the moment. So remember, the complete writing of the equation of equilibrium here is sum of moments, capital M, about which point? About point A, and we're taking anti-clockwise as positive, all equal to 0. All right, so then if we apply that equation and we look at our problem, we've got P2 here, its moment about point A, perpendicular distance is 3, so P2 times 3, tending to cause a clockwise rotation about point A, so therefore negative. So we have the negative sign out the front. All right, so what's our next one? I've just started to draw. So looking at P1 over here, just drawing in my components just for reference. So horizontal component here. So if we draw our little triangle, right angle triangle here, this length here will be P1 sine 30 because this is the opposite side to the 30 degrees here. So P1 sine 30, and this component down here is P1 cos 30. Right? Again, note how I've drawn my components so that their line of action passes through the correct point. Okay, so putting that into our equation of equilibrium, we've got P1 sine 30. So this horizontal component here, perpendicular distance to point A is this distance here, 4. And that will tend to cause an anti-clockwise rotation about point A. So that one's positive. So I'm going to put a plus out the front. And now if we consider the other component here, we've got the vertical component, P1 cos 30, perpendicular distance of the line of action of this force to point A is this distance here, 6. Okay, so that's what we've got. And it's tending to cause a clockwise rotation about point A. So that's another negative one. And now we've got the moment, the applied moment to deal with. It's clockwise, as shown, so minus M1. And that's it. So put all that, we've got to put our unknown in, right? Okay, so over here, we've got our unknown force RB. We can try and work out our perpendicular distance here from the line of action of RB to point A. It's not that difficult in this case, but generally we'd use Varignone's theorem and break this thing up into components. So we will have here, again, just putting those components in, again, making sure that we keep their line of action correct. Don't put RB sine 40 or RBY out here, for example, or RBX down here. Right? Put them where their line of action is correct. So we have RB cos 40. Its perpendicular distance is 4. And it's tending to cause an anti-clockwise rotation about point A. So that one's positive. The vertical component of RB sine 40, its line of action passes through point A, so we don't have to worry about that. And now we're all equal to 0. And the solution has run on a little bit further than I wanted it to there, but I've just rearranged that equation here to find RB. Right, so I've just rearranged that. So if we put the values into the calculator, we get 8.613 kilonewtons. Okay, so remember to carry 4 significant figures, or at least 4 significant figures, through all of your calculations to minimize round-off errors. You can carry more if you want, but at least 4 should be carried through your calculations. Okay, so now we look at our other equation of equilibrium. So this one's usually a little bit easier for most people. And this, again, the solution has run on a little bit further than I really wanted it to, but anyway. Sum of the forces in the x direction equals 0, to the right is positive. So we just need to work through all of our forces here. So RAX going in the negative direction, so minus RAX plus RB cos 40, this component here, plus P1 sine 30, the horizontal component of our force P1 here, all equal to 0. Now, what I see a lot of students do is to, let me see if I can rub a couple of things out here without making a big mess of my solution. All right, so they'll write the equation of equilibrium like this, okay, without putting the equals 0 here, right? So strictly speaking, that's not correct, right? You need to have equal to 0. Right? So the correct way to write your equation, sum of the forces equal to 0, then have all of your forces equal to 0, and then rearrange to solve for your unknown, okay? So if we do that and substitute in our unknown values, you get RAX equals 7.6, yeah, roughly. And if we then go and do the same thing for some of the forces in the vertical direction, again, writing it correctly, sum of the forces equals 0, and then we apply that equation. So we have RAY, our unknown up here at point A, minus P2, minus the vertical component of P1 cos 30, plus RB sine 40, so the vertical component of our force here at B. All equal to 0, rearrange that, and we get RAY equals 0.2 kilonewtons. Okay, so now we need to check our answers. So if we go to the next page, I've just copied over my free body diagram. You don't need to redraw it at this point in time in your solution. I've just put it here so we can refer to it without having to go back to the previous page. So again, apply equation of equilibrium. So previously we used point A to start with. So this time we're going to take moments about point B. And let's have a look at what we've got. So starting here with taking moments about point B, we've got P2 times its perpendicular distance to point B is 3 meters here, and it's tending to cause a clockwise rotation. So we push down on here, and if we hinge about point B, that's going to rotate clockwise, so therefore that's going to be negative. Then if we look at our vertical component of the force P1 over here, P1 cos 30, perpendicular distance to point B is 6 meters, and again tending to cause a clockwise rotation, so again negative. We've also got the M1 applied moment here clockwise, so that's negative, put that in, and then we've got RAX up here. Perpendicular distance to point B is 4 meters. So that's our perpendicular distance here, tending to cause an anti-clockwise rotation about point B, so that one's positive. RAY, its line of action passes through point B, so no moment there. So we can put that all equal to 0, rearrange the equation, substitute our values, and solve for RAX, and we get the same value as we got before. So if you get a different value, then either your equation here is wrong, or the one that you got on the previous version of the solution was wrong. Okay. So here I've just continued through and just redone the force equilibrium equation. Sorry about the dinging of my phone in the background there. So this is pretty much the same as we had before. I won't spend too much time on this. The video is a little bit long already, and I don't want to go through the next bit. All right, so now that we've gone through our checks, we report our final answers. So I've just said there at the bottom of the page here, we've got the same answers that we got before, so should be okay. So what this tells us is that we've got our algebra correct in both cases, and we've written our equations of equilibrium correctly in both cases. What it doesn't tell us is whether we've got our free body diagram wrong or not. Okay, but just by going through this analysis twice and doing it in two different ways might help you to realise that you've got something wrong in your free body diagram. Okay, so now we should report our final answers, and now we need to round up to an appropriate number of significant figures. And for most engineering problems, 3 significant figures is appropriate. Any more than that is telling lies. You don't know your answer to any better than plus or minus a few percent, because you don't know your input values to any better than plus or minus a few percent. Okay. You know, and in reality, probably 2 significant figures, but you know, 3 significant figures is okay. All right, so that's that part of the solution, and I've just indicated here the directions of those reactions that we've got that the supports exert on our truss frame. All right, so the next part of the problem was to determine equivalent force and moment at the pin joint, equivalent force and moment here. And then after that, determine the equivalent single force. So you start with a force and a moment here, convert that into, or find the equivalent single force acting somewhere. And here I've said to specify where its line of action crosses a horizontal line through here. Okay. And then as an extra check, and also to show you that all of these forces or different systems of forces and moments are equivalent, use just the single force to calculate the reactions again to check the previous solution. Okay, so first let's look at determining FRX. So we want to, what is the equivalent to all of these forces and moments here? So we look at finding the resultant of the x components of all of the forces, and I've just redrawn here the coordinate system for reference. In the x direction, the only force that we have is the horizontal component of P1. Okay, so I'm not going to spend too much time on this. We did this in the previous, how to work out these components. We did this in the previous part of the video. And then our resultant of the y components. So here we've got P2 plus the vertical component of P1. Okay. And they're in the negative direction. We do the calcs for that, and we get those 2 reaction components. And to find the resultant, we just do the square root of the sum of the squares. It's basic Pythagoras, high school maths, and we get 5.82 kilonewtons. And I've just drawn that over here. So we've got FRX to the right, FRY downwards, and our resultant looks something like that. And if we want to find the angle in here, we just use the inverse tan of opposite over adjacent. So the opposite side of this triangle here is FRY, the adjacent side is FRX. Put in the values and get about 80 degrees. All right, so now we need to look at the resultant moment. So this point up here we call point A. So, and we're taking anti-clockwise as positive. So look at the resultant moment. So we need the sum of the forces times their perpendicular distances plus any applied moment. So we've got 1 in this case. All right, so let's go through this. So we've got P2 here times 3, and it's negative as we discussed before. And then we have P1 cos 30, so the vertical component here, times 6, again clockwise, so negative. And then we have the horizontal component times its distance here, 4. So, and it's tending to cause an anti-clockwise moment about point A. So that's a positive one. And then we have M1, which is clockwise, so negative. Okay, all right, so if we now substitute all of our values into that expression, we get our resultant moment, which is minus 26.39 kilonewton meters. Okay. All right, so if we show that over on over here, so I'm just showing the resultant force and moment that are equivalent to those two forces and moment that we had originally. Oh yeah, so this is just showing that left-hand side of the truss there, not showing all of it just to simplify my diagram. And now what we want to do is to find the location where we can have just a single force that's equivalent to this force and this moment. Right, so we can see that we've got a moment clockwise. So hopefully you can see that we're going to have to move this force out to the right somewhere, okay, to get for this force to cause a clockwise moment about point A. Right, so we want to know where the line of action crosses this horizontal line here, just to the right of B. So if we call that X, and I'm just putting on the components there just for reference, and also my coordinate system. So we want the moment due to this reaction force here to be the same as MRA. So if we've got FRY times X, tending to cause a clockwise moment, right? And we just put negative in front of our two terms here. But we need also, because we're looking at the force down here, we've got the horizontal component FRX to include as well. Right? So FRX, its perpendicular distance to point A is 4, and that's tending to cause an anti-clockwise moment. So we make that positive. So rearranging our equation to solve for our unknown distance X here. Put in our values. Now this is a bit tricky. Some of you might be tempted to put in minus 26 here and minus 5.732 here, because that's what we had on the previous page, right, for these values. So we don't do that here because we've already taken into account the fact that these are causing negative moments by looking at our diagram here. Okay? So that's one of the tricky things with moments and forces, right? It's not just the sense or the sense of the force and whether it's positive or negative that matters. It's the direction of the moment that it causes, or the direction of the rotation that it causes. So here we've already taken into account, right, this FRY and this MRA here causing clockwise moments. So we've already put them here. So if we put the values into our calculator, we get 5.302. And now if we redo our equilibrium equations using our free body diagram, now it's just an equivalent single force, which is now down here. All right, so we don't show the other forces that we had originally. This force here now on its own has the same external effect of those two forces and moment that we had originally. So let's take moments about point B here. We could have taken moments about A, doesn't really matter. I've just taken moments about point B. So we've got RAX times 4 tending to cause an anti-clockwise moment, so that one's positive. And then we have FRY So the vertical component of FR here times X, this distance that we just found, and that's tending to cause a clockwise moment. So it's negative here, all equal to 0. Right? So all of the other forces have no moment effect about point B. So rearrange that, put in the numbers, and we get RAX equals 7.598, the same as we had before. And we can just redo our force equation, force equilibrium equation. So FRX up here, where is it? FRX down here, plus RB cos 40 minus RX, or equal to 0. So we just solve for RB this time, and we get the same value that we had before. And do the same thing for the forces in the y direction, all equal to 0. And put in our values, and we get 0.2 kilonewtons, the same as we had before. Okay, so this not only is a check of what we've done before, but also shows you or demonstrates that this single force here that we've determined is equivalent to our 3 external loads that we had before, the 2 forces and the moment. Right, so I've just got done it again here. So instead of finding the location in the of the resultant force here, down here, I've found it up here. I'm not going to, already taken too long with this video. So this is the same as we had before. It's all the same, just repeating that there, so you don't have to worry too much about that. So now finding the result, oh, this is the same as before, yep. But here, I want to find the position of the resultant force above point A on this vertical line. So go through the same process that we did before. Here, let's just go back a step. Right here, we got 26.39 meters, so like way, way above here. And that makes sense because if you remember, we've got a force acting down here, or the original force with a force up here, force out here, a moment out here, all tending to cause a clockwise rotation, right? So for this equivalent force to have the same moment effect as all of those 2 forces in the moment that we had originally, this force has to be way, way up here above A. Right, so just redoing my free body diagram again with the single equivalent force. Some of the moments about A, so I did moments about A this time and found RB, so similar to what I did originally, and got the same value there. Some of the forces in the horizontal direction equals 0, and this is all the same as previously, right? And we end up with the same values. Okay, so I hope that was helpful. It's quite long to go through all of that, yeah, how you do rigid body equilibrium problems, how you check your answers, looking at using different points to calculate moments, and also going through how to determine equivalent systems. So going from multiple forces and moments to just a single force and moment to just a single force. All right, that's it for now. See you in the next one. Bye for now.